Hello everyone and welcome to MV Tutors. I'm Salo and I'll be looking at the memo for the physics prelim exam written in Gauteng. And yeah, without wasting any more time, let's get right into it. Do not forget to like our videos as well as subscribe to our channel. Alright, question 1. Let's look at the multiple choice. Can be tricky, but let's see if we can predict the flops. So it says, an air bubble in a tank of water is rising vertically at a constant velocity. Okay, constant velocity means acceleration is 0. The forces acting on the bubble are x, y, and z as shown. So the diagram is not drawn to scale. Okay, so which option is incorrect with respect to the 3 forces acting on the air bubble? Alright, so I see then what I'm going to do, I'm going to say the sum of the forces in the y direction are equal to 0 because there is no acceleration, right? What do I mean by that? So if I take up as positive, I would have x minus z plus y. And that, remember the sum of force is equal to mass times acceleration, but because acceleration is 0, as we have established, then it's equal to 0. And then I could say that x is actually equal to z plus y. So let's see. A, x is equal to y plus z. Yes, that's correct. B, z is equal to x plus y. No, if I were to write this in terms of z, z would be x minus y. So B is not correct. C, y is equal to x minus z. Let's see. Y, yes, if we take z to the other side. And then x is bigger than z, which is bigger than y. Yes, the fact that this thing is moving upwards means that x is indeed bigger than z. And you can see according to the arrows, even though they're not drawn to scale, that z is bigger than y. Okay, so D is correct. So the only incorrect one in this case then would be B. So that was 1.1. Now 1.2. The elevator question. Remember that elevator video I did? Go and watch it. I will also put the link there. Alright, so a person stands on a scale in a lift. The motion of the lift is given in terms of its acceleration. Okay, remember, whenever we're looking at lift or elevator problems, we have this one general equation, right? The normal force is equal to the mass times acceleration, but we have acceleration, and then also we have gravitational acceleration. So that's the formula that we're going to use. Now it says the motion of the lift is given in terms of its acceleration. Which situation represents weightlessness? Okay, basically I'm gonna look at all options. Okay, just do that. So for A, we have a constant speed, so acceleration is 0. If I'm looking at this equation, if acceleration is 0, I only have mass times gravitational acceleration. Okay, so that is not weightlessness. If I look at B, upward acceleration, so my normal force is going to be the upward acceleration. It will be 9.8 plus 9.8, right? So basically that's 2 times the gravitational acceleration times mass. Okay, and if I look at C, downward acceleration, same thing. Okay, but now the acceleration is negative. So here we have 0. Okay, so basically, there we have our weightlessness. But let's just check D. Downward acceleration of 5. Okay, that's okay. We have minus 5 plus 9,8. It will be equal to some answer. But basically, C is the correct answer over here. Alright, now let's go over to 1.3. A golf ball falls vertically downwards. So it falls, right? So you have a ball, it goes all the way down. It falls vertically downwards from rest. So we know that our initial velocity there is 0. And bounces back to the same height. Okay, so this would be your ground, right? and then it bounces back to the same height from which it was dropped. Wow. The graph below shows the acceleration of the golf ball with time. Yes, so acceleration is always constant, right? We have acceleration as 9.8 meters per second squared. But as soon as it touches the ground there, okay, that's where you have that dip. Okay, so it's constant, and then where you have a bounce, that's where you have the dip. Okay, that's how you normally illustrate that. Alright, so all effects of friction are ignored. Now, the following statements are made about the golf ball's motion. It experiences maximum speed at minimum height. Yes, remember, it started off at 0, right? But by the time it reaches the ground, it's at its maximum velocity. Okay, and then by the time it gets back up again, then we're back to 0 because it's the same height. Okay, so 1 is correct. 2, its displacement falling is equal to its displacement rising. I would be quick to say, yeah, definitely. I mean, it does fall from the same, it would fall from the same height and then bounces back. Sorry, yes, it falls from the same height, it bounces back to the same height. So, but here we need to be careful. Okay, displacement, remember, it consists of magnitude as well as direction. So in terms of magnitude, yes, that's true. But in terms of direction, no, it doesn't go back to the same direction. It didn't bounce here and then go back there. It went in the opposite direction. So direction, no. So option 2 is not correct. And option 3, it experiences minimum speed at the maximum height. Yes, it does. Okay, so only the first option and the third option are correct. And if we have a look at the options available to us, that will basically be option B. It will be B. Now 1.4. A ball of mass m moving with a velocity v collides head-on elastically with another body of the same mass moving with a velocity in the opposite direction. So basically you have that one going in this direction, I'll call it A, and then you have B going in the opposite direction. They both have the same mass, they both have the same velocity, just in opposite directions. And they told us it is elastic, right? So the head-on collision is elastic. So what we know then is the sum of kinetic energy before is equal to the sum of the kinetic energy afterwards. Alright, so yeah, let's see. So after the collision, both balls move with velocity v. So both balls move with velocity v. Like together? It's not certain. So option B, both balls travel in the opposite direction with the speed v. Yes, that's what we know. They do travel in the opposite direction. Okay, but now they're not telling us. So this is after the collision. Oh, okay. After collision, both balls move with velocity v. No, remember velocity is also, what do you call this? It's a vector. It has both magnitude and direction. So yes, they have the same magnitude v, but not the same direction. So yeah, A, I'm gonna just ignore. B, both balls travel in the opposite direction with a speed v. Remember, speed is magnitude, so yes. C, both balls move at right angles to their original direction of motion. I'm not so certain about that. I don't think so. And then D, one ball comes to rest and the other ball travels back with a velocity of 2v. So it just steals or takes away. No, because they are the same mass, no. If maybe it was different masses, yeah, but no, in this case, I mean, yes, one could come to rest and the other could travel back, but I doubt it would be at the same velocity. All right, so no. So then our answer would be option B. All right, 1.5. A mass is lifted from rest on the ground to point H as shown below. All right, so we can see. So P is the increase in gravitational potential energy of the mass. K is the kinetic energy of the mass at point H. All right, so what happened, right? When we were at the ground, there was no potential energy, since they're talking about gravitational potential energy. Why? Because your height was 0. And then also there was no kinetic energy. Why? Because your speed or velocity was 0. Okay. And then once it is lifted up, so I'm going to say in the lifted scenario, your potential energy will be your mass times gravitational acceleration times the height. Your kinetic energy will be half mv squared, because there is some movement, right? So there is a velocity. So now it says, which expression is equal to the mechanical work done on the mass to move it from the ground to point H? So we know that mechanical energy, E mech, is equal to the change in kinetic energy plus the change in potential energy. And we know that is basically final minus initial plus potential energy final minus potential energy initial. So we know that initial is 0. Okay, so what we have then is your kinetic energy final, which is the half mv squared, and the potential energy final, which is mgh. Okay, so basically it's E plus P. Sorry, what am I saying? It's K plus P. K plus P. So yes, we have option A over there, which is P plus K. Yes. B, no. C, no. Definitely not D. So we're going to go with option A for 1.5. Now 1.6. To what does the term redshift refer? Remember redshift? The color red, longest wavelength, smallest frequency, far away. Whereas when you get to the blue side, blue shift, also check out that video if you are not certain, the red and blue shift Doppler effect video. I'll put the link in between, not in between, I'll put the link in the description. All right, and then you have the blue shift, where it has the highest frequency but the shortest wavelength. So options A, an object's speed in space. No, we don't refer to the speed. B, the color of a distant galaxy. No, definitely not. The expansion of the universe. Remember, red shift, biggest wavelength, smallest frequency. So it just shows the expansion of the universe, which is correct. And the increase in an object's temperature, definitely not. Okay, so C is our answer there. 1.7. Which of the following graphs has a slope equal to Coulomb's constant K? Okay, let's go back to the equation. So if we look at the electrostatic force between two charges, we have this formula over here, right? And if we're going to write it in terms of K, basically you have F r squared over Q1, Q2. Okay, so that is K. Which of the following graphs has a slope equal to Coulomb's constant K? All right, so we have our equation that we have K. Now, if we look at A, remember the gradient of option A, gradient is change in y over change in x, right? So what is our change in y over here? So we have change in E over change in Q1. Okay, now option B, the gradient there will be change in E over change in r squared. If we look at option C, we have change in E over change in Q1 over r squared. And then option D, we have change in E over change in Q1 over R. Okay, so I see E here. Remember what E is? Geez, did I forget? E is, I think it's Q over R squared. Okay, let me just check in the formula sheet. Ooh, let me not write lies over here. Okay. So E is KQ, I forgot about K. KQ over R squared, or basically it's equal to F over Q. Okay, let's go back to our question. Okay, there we are. So if we're going to write this K in terms of E, what can we do? So we know that E is F over Q. So this portion over here, I can put it as E, right? So we have E over Q. There's one Q left. And then we have R squared. So where does it actually, which option does it actually go well with? So we have E over Q, we're missing R squared. Here we have E over R squared, we're missing Q. Here we have E over Q, R squared, actually this R squared can go up there, so yes, option C is giving. Then we have E, QR, we're missing an R squared, so no. So our option here, I hope you see it nice and clear. We basically have E, R squared over Q1, that's option C, right? So C is the correct answer. 1.8. 3 resistors are connected in a circuit as shown in the diagram below. I actually made a video using Phet simulation, okay? So the answer is there if you want it to be explained in detail using a simulation, which is actually, it works quite well with electric circuits if you don't understand it that well. But anyway, 3 resistors are connected in a circuit as shown below. So we have 2 that are in parallel and we have 1 there. Alright, now it says a 4th resistor is connected parallel to the 4 ohm resistor. Alright, so we have there another one. We don't know the value of it, doesn't matter. Now it says, compared to the original circuit, how will the power dissipated by the 8 ohm and the 4 ohm resistors change? Remember, we have a certain current, right? That current divides once it gets here, and then it goes back to normal again. Now, beforehand, we had a higher current going through the 4 ohm resistor. Okay, so with an addition of another resistor, the current now has to divide again. So the power for the 4 ohm resistor would have to reduce. Remember, power is equal to velocity times current. Okay, so that's what did I say velocity? voltage times current. All right, so yes, because the current will have decreased, I'm expecting the power for the 4 ohm resistor to also decrease. Okay, now overall, let's see what's happening overall in the circuit. So if you introduce another resistor, so remember, if we're looking at the total resistance, it'll be the parallel resistance times the 4 ohms resistor, right? Or resistance. And then, should have actually just written it as 4 ohm. All right, so now, this is the scenario beforehand. Scenario afterwards, this total resistance, I will have that parallel resistance there, but because now I have another parallel resistance, so this 4 ohm will actually go down. Okay, so the total resistance overall will decrease. Now, if the total resistance overall decreases, our current that actually passes through here will have increased. And if the current has increased, it means when it's shared between the 8 ohm and the 10 ohm, it would have increased, right? So the power there through the 8 ohm would have increased. Okay, so the power has increased because our current has increased. Whereas through the 4 ohm resistor, because now our current is divided, it has decreased going through the 4 ohm resistor, the power will have decreased. So therefore the options that we have, 4 ohm resistor, we're looking at decrease, which is option A and D. But for A, it says the 8 ohm resistor decreases, which is wrong. So we're going to go with D. Okay, because the 8 ohm resistor's power increases, whereas the 4 ohms power decreases. We are almost there now. We're at 1.9. It says an immersion heater can be operated either from an AC power supply or a DC source. The graph below represents the potential difference of an AC power supply. As soon as the graph that you see is sinusoidal, then you know you have alternating current. But if it does this, then we're looking at direct current. Okay, so now it says, what DC supply voltage would produce the same rate of heating? So if you want to convert, or you want to see what the DC power DC supply voltage is from an AC power supply, then you would use the root mean squared knowledge. Okay, so what DC supply voltage would produce the same rate of heating? So I would use the equation then. The voltage would be your Vmax over root 2, right? The root mean squared. And we can see our Vmax is 12. And then we have root 2. Yeah. So that's basically, we don't need to calculate. I was about to take out the calculator. But I can see then the options: A, no; B, no; C, yes; D, no. So yeah, our answer there is C. And finally, the last question, 1.10. The work function of a metal is that. Okay, so the work function is Planck's constant times that frequency over there, threshold frequency. If this metal is illuminated with light of frequency 3 times FO, or threshold frequency, the maximum kinetic energy of photoelectrons will be, okay, let's go quickly to the formula sheet if we have forgotten there. Okay, so maximum velocity, I see that we have E is equal to the work function, the energy, plus the maximum kinetic energy. All right, let's go back to the question. So we were told that, okay, the work function, we have it, we've written it down. It's just Planck's constant times the work, the threshold frequency, and then our EK max, which is what we're looking for. So what about the energy? So now it says if this metal is illuminated with light of frequency 3 times FO. So remember, E is equal to H times F, and they told us that the frequency is 3 times. Sorry, they told us that the frequency is 3 times the threshold frequency. So basically we have 3 HFO. All right, so then if I solve for our maximum kinetic energy, it'll be 3 minus 1, which is simply 2 HFO. And if we look at that, if we look for that answer, it would be option B. We had a lot of B's today. And that's it for question 1. Alrighty, question 2. So a toy train of mass 2 kilograms, okay, just put it there, and a toy car of mass 1 kilogram are attached by a light inextensible string. The car train system is pulled up a rough slope. Okay, so this is rough. We're expecting there to be a coefficient of kinetic friction because they're moving. A rough slope at a constant velocity. So constant velocity means that the acceleration is 0. By the rope with a force T2. Okay, so we have that tension. Acting on the rope at an angle 10 degrees. At a 10-degree angle to the inclined plane. Okay, so a toy train of mass 2 kilograms and a toy car of mass 1 kilogram are attached by a light inextensible string. The car train system is pulled up a rough slope at a constant velocity by the rope with the force T2 acting on the rope at a 10-degree angle to the inclined plane. Sorry, I had to read that again to realign myself. So, 2.1, explain the term net force or resultant force. I'm not going to write this down, I'll just say it out. So basically, the net force on a body is the sum, right, of all the forces basically that are acting on it. Okay, 2 or more forces acting on that particular body. All right, so yeah. And then 2.2, draw a labeled free body diagram for the toy train. While doing that, also just do it for the car as well, because you never know these questions, if they need other free body diagrams. But anyway, let's just focus on the train. So if that's your inclined slope, there at 20 degrees, there is your train. Ooh, this 20 degrees is very steep. So what always acts vertically downward is your gravitational force, and what always acts perpendicular would be your normal force. Okay. And then we have that T2 that's pulling. So I'm just gonna do that, right, so that I can align myself properly. Then I have that T2 force, right, that string pulling it up, and that's at 10 degrees. I see it's 5 marks, so I'm assuming I need to have 5 forces there. Then we have T1. All right, so I'm just gonna draw T1 there. And remember, this is a rough surface, so there must also be friction force. Because these are going up, I mean, they're not really finicky about the lengths of the forces, but I would put T1 as well as the friction force less than T2, because ultimately this whole system is going up the slope, right? So yeah, okay, so that's your friction force. And yeah, we have 5 of them. We're not going to resolve anything at this point. We'll probably come back to this free body diagram if we need to do calculations, which we'll probably do. All right, so that is that for 5 marks. 2.3, the tension force T2 is increased to 20 Newton. Okay, so we have that information, 20 Newton, causing the system to accelerate up the slope. Okay. Calculate the magnitude of the acceleration of the system if the friction force acting on the car is 1,5 Newton. Okay, and that on the train is 2 Newton. Alright, so the friction force on the train is 2 Newton. Okay, so we need to find out what that acceleration is. Like I said, yeah, the free body diagram for the car is also necessary. So let's just do that for the car. Again, we have our gravitational force, we have our normal force, we have T1 pulling it up, and then we have the friction force taking it down. All right, and because now we're doing calculations, I think this is where I want to now resolve things in their x and y components. Okay, so here we have FG, because we have our theta there, which is 20 degrees. I would just say cos 20 degrees. And then on the side we have FG sine 20 degrees over here as well. Actually, instead of putting FG, let me rather just put, because now it's 2 FGs, which one is which? So for the car, I'll have 1 times 9.8. Okay, so 1 times 9.8, that's the mg, times cos 20 degrees. And there I'm not going to put the 1 times, we already know that's 9,8 sine 20 degrees. And over here, for the train, I'll have 2 times 9,8 times cos 20 degrees. And then I also have 2 times 9,8 times sine 20 degrees. But there's also that T2 that needs to be resolved, right? I hope this color shows. So here we have T2, which is basically 20. So I have 20. Okay. So I have 20 sine 10 degrees, and over here I have 20 cos 10 degrees. Okay, I hope that is clear. Now let us start to calculate. It's just a matter of putting there the net force or resultant force. Okay, so our resultant force, according to Newton's second law, if resultant or if net is equal to mass times acceleration. Okay, I'm gonna start with the train and get the equations there. And if I have two unknowns, then I know that I need to use the car as well. So with regard to the train, if I resolve, it's a busy drawing, but we have one force going up and three forces going down. So basically, I have 20 cos 10 cos 10 degrees if I choose going that way as positive, and minus 2 times 9,8 cos, it's sine 20 sine 20 degrees minus T1 minus the friction force, which is for the train, that's 2, and that's equal to the mass, which is 2 times the acceleration. All right, okay, we could have said T2 cos 10 minus FG sine 20 minus T1 minus F of K. And okay, if you wanted to start like that. Now let's just use the calculator to get values. All right, and now I'm just shift it there. So I have 20. Make sure that your calculator is on degrees and not radians. So 20 cos 10 minus 2 times 9,8 times sine 20 degrees minus 2. Okay, I get 10,993. Okay, so 10,993. I actually want to put 11. And we have minus T1. I'm going to take T1 to the other side and just say minus 2A is equal to T1. So I see I have two unknowns. So I'm going to go over to the car and see what's what. All right, same thing. Resultant force is equal to mass times acceleration. By the way, both the car and the train will have the same acceleration. Okay, so we have T1 minus, I was going to say FG sine 20 minus the friction force is equal to 1 times the acceleration. So it's T1 minus 9,8 sine 20 degrees, and for the car it's 1,5, which is equal to the acceleration. I'm gonna now say T1 is equal to 9,8. Let me save this answer, store it as A. Okay, cool. So 9,8 sine 20 plus, because when it goes to the other side it will be plus 1,5. It's 4,85. So I have 4,85. Let me round it up to 3 decimal places. 852, and then plus the acceleration. So I have equation 1 over here, and I have equation 2, and I've written both in terms of T1. So basically I can then say 10,993 minus 2 times the acceleration is equal to 4,852 plus the acceleration. If I take acceleration to the right, I have 3A, and if I take 4,852 to the left, so it will be, no, not shift, it will be alpha A minus the answer, which is equal to 6,14. Alright, and I'm going to divide that by 3. and I get an answer of the acceleration is 2,05. I'm rounding off to 2 decimal places at the end. So meters per second squared. Do not forget your units. Whew, all right, 5 marks. There we go. We have the acceleration. And now 2,4. So it says halfway up the slope, the string T1 breaks, right? Meaning the car rolls down the slope. Does the friction force on the train increase, decrease, or remain the same while still moving up the slope? I mean, if you think about it without thinking too much, you'd be like, well, what does friction consist of? But in your head, you're thinking the car has lift. So the train is not pulling that much anymore. It will actually accelerate or shoot up more, right, up the slope because there's less baggage. But that doesn't really refer much to the friction. It's more on the weight, or rather the tension force T2 will probably increase. Hence, the acceleration will increase as well going up the slope for the train. But here we're talking about friction. So what I would suggest is when you get questions like these, please write down the equation for friction and see what actually changed here. So the friction force is equal to the coefficient of friction multiplied by the normal force. What does the normal force consist of? The normal force is basically, if we're looking at our free body diagram for the train, the normal force is going to be equal to, yes, it's going to be equal to your FG perpendicular, right? So it's normal force plus T2 sine 10 degrees will be equal to that. So yeah, minus T2 sine 10 degrees. Now, if the car moves or is shut off, right, it affects T1, right? So will the normal force change? This will still be there. There's still that tension, okay? So in that case, the normal force doesn't really change. And then when we look at the coefficient of kinetic friction as well, that doesn't change because that is affected by the type of surface that we have over there, okay? That didn't change, okay? And then the slope of this, the slope of this, what is this? This driveway hasn't changed as well, okay? So with that being said, will the friction force on the train increase, decrease, or remain the same? I would say it would remain the same, okay? And to explain the answer, I would then say the normal force didn't change, all right, as well as the coefficient of kinetic friction, that also didn't change, okay? Both have stayed the same. So hence, the friction force will also remain the same. And that's where we say we're done with question 2. Question 3. A tennis ball falls freely from rest from point A, which is 44 meters above the ground. The time taken to fall to the different points or positions B, C, and D is given in terms of time t, as shown below. Ignore all effects of friction. Okay, I like drawing what is happening. So there we are at point A. This ball with time falls until it reaches D, right? So this is A, that's D. And then the height or the depth which it fell was 44 meters. And then when it fell, it was actually dropped. It was from rest, so the initial velocity is 0. Final velocity there is its maximum velocity, right? We don't know what that is. And then we have points B and points C. along the ride, okay, until it gets to the bottom. Yeah, something like that. Okay, so now we can go ahead and start answering questions. Now 3.1 says define the term free fall. Alright, so free fall, loosely explained, basically there's no other force acting on this projectile apart from gravity. Okay, or you want to be more technical, you could say it's the motion of a body when the only force acting on this body is gravitational force. And then 3.2 says calculate the value of t. So we're going to go to our equations of motion. What do we have? We have, by the way, I'm taking downwards as positive. We have delta y as 44 meters. Our gravitational acceleration is positive 9.8 meters per second squared. And our initial velocity is 0. That's what we have, right? Let's just go over to the equations of motion and see which one will actually help us to find what the time is. So I'm going to look for one with delta y and only initial velocity. So the equation we're going to use is delta y is equal to initial velocity times t plus half, I'm going to put a g there, delta t squared. Okay, and what do we have? Oh, scrolling the wrong thing. So what do we have as initial velocity? We have 0. Okay, so I'm not even going to put that delta t there. And then we have a half times 9.8, and we are actually looking for t. And then here we have 44. So basically delta t, if we do some mathematics gymnastics, it's 44 divided by a half times 9.8, and all of that is rooted. We're only taking the positive because we're not dealing with negative time over here. So in there we have 44 divided by a half times 9.8. Okay, and we're getting 2, oh wait. Whew. So our time actually is, okay, we'll get there. Let's just write delta t. It's equal to 3. Okay, I am not even going to try to round off to 2 decimal digits. We're going to get back to t. But remember, delta t, in our case, for the entire duration from A all the way to D, will be 2t plus 3t. So basically, it took place for 60 seconds. So not 60, but 6 dot t seconds. So basically t will be equal to 0.5 seconds. Okay, so let's just I think I almost forgot it there. So 0.5 seconds, or a half. Maybe let me just put 0.5 there. Make sure the S and the 5 actually look different. Alright, and 3.3, it says calculate the height of the ball at point C. So the entire duration took 60 seconds, or 0.5 seconds, but now the height at point C. So here, until we get to C, we have 2t plus t, so we have 3t. Okay, which is basically 3 times 0.5, which is 1.5 seconds until we get to C. So let's just write there that we have delta y. We're looking for delta y, right? So we're looking for our time is 3 times t, which is 1.5 seconds. What else? Our initial velocity is 0. So I think we're still going to use the same equation. Okay, let me just put this there. So we have delta y is equal to initial velocity, which is 0, times time, which is 1.5, plus a half, 9.8, and then we have 1.5 squared. Alright, so we have 0,5 times 9,8 times 1,5 squared, and we have there 11,025. Okay, so are we done? Did we get, what is this 11 that we just got? This is that height, so from A all the way to C, okay, because we're still going down. So that height there is 11,0, wait, is it? Yeah, it's 11,025 meters. Okay, they asked for the height of the ball. They didn't ask how far down did the ball drop, so we're basically looking for this height. Okay, so therefore the height is the 44 minus 11,025. So we're gonna say 44 minus the answer. It's basically 32,98 if I round it off to 2 decimal places. Okay, so for the visual learners, it's important to, as you keep getting answers, just, populate your thing so that your sketch, so that you know what you just solved, what you need, and so forth and so on. All right, we're almost there with question 3 now. Question 3.4. It says, if after the first bounce the ball reaches point C, sketch the position time graph for the ball from the moment it is dropped until it reaches point C after the bounce. Okay, show the following on the graph: the time values at point D and C before the bounce in terms of t, the heights at A and C, take the ground as point of 0 reference. Okay, so I'm gonna just put there our graph. Okay, so we have that. This is now displacement, no? Position time graph. So I'm gonna say delta y in meters, and we have time in seconds. So what I'm going to do, this thing was dropped, okay? So it was dropped. Let me use a different color. It was dropped. And then it spent a little bit of time on the ground, and then it went back up again to position C. So where it was dropped, we had 44. Let me just write this on top. So we were at 44 meters, okay? And then we had point B and point C. So point C, we said it was 1,5. By the time it reached the ground, it was 0,5, right? 0,5 seconds. Oh, let's put it in terms of t. So by the time it reached the ground, it was actually 6t. All right, and then C is at 3t. So that's halfway. Ooh, so that is where point C is. Okay, then maybe I should sketch this one a little bit different, because it needs to go back to C. Okay, if this is C over here, so we went all the way to C. Okay. All the way to C. So what was the height then at C? We did say it's 32,98. We could round it off to 33. All right, what else do they want? So the time values at point D, so yes, that's where D is. And C, yes, that's where C is. we have our 3t there in terms of t, and then take the heights at A and C. So that's where A is, and then C. And then that's it. That is the 5 marks that they want. And with that, we are done with question 3. Question 4. A wooden block of mass 150 grams is freely supported on brackets at a height of 2 meters when a bullet of mass 50 grams is fired vertically into the block as shown below. Alright, just convert the mass there for yourself while you're at it, because we're dealing with kilograms when we do calculations. And 50, you can say 0.05 kilograms. We see that it's shot there at 200 meters per second. That is very fast. All right, as expected, it's a bullet. So yeah. So it says the bullet embeds itself into the block, and the bullet block system rises vertically into the air for a few seconds and then falls back to its original position. Okay. And the first question, state the law of conservation of momentum in words. So that law says the total linear momentum of an isolated system remains constant. Okay, that's it. Total linear momentum of an isolated system remains constant or is conserved. Now, let's go to 4.2. It says, calculate the magnitude of the velocity of the bullet block system after the bullet becomes embedded in it. Okay, so we're going to look at momentum before. Okay, the sum of the momentum before is equal to the sum of the momentum afterwards. So before we had the wooden block, so the mass times the velocity, that's momentum of the wooden block, I'm just going to say WB, plus the mass times the velocity of the bullet, I'm just going to say BU. And that is basically before, or initially, basically is equal to the mass of the wooden block plus the mass of the bullet, because they're both together now. And then we have that final velocity. Okay. So the mass of the wooden block, that's 0.15. The velocity is 0 because it's stationary. The mass of the bullet is 0.05, and its velocity initially is 200 meters per second. And then here we have 0.15 plus 0.05, and we are looking for that velocity. So if I were to write this equation in terms of the velocity, I would say 0.05 times 200 divided by 0.15 plus 0.05, and we can then calculate what the final velocity of the system is. 0.05 times 200 divided by 0.15 times 0.05, and we get our answer. No, oh my gosh. Plus, oh yeah, so we get our answer as the final velocity of 50 meters per second. Okay, it's the final velocity. And then now 4.3. Now, is the collision between the bullet and the block an elastic or inelastic collision? Explain by using a calculation to justify your answer. So here we know that if something is elastic, so the elastic condition says that the sum of the kinetic energy initially must be equal to the sum of the kinetic energy at the end. Okay, so what happened? I'm going to look at initial conditions, initially, and then finally, and let's see if both yield the same answer. If it does, then it's elastic. If it doesn't, then it's inelastic. Okay, so what do we have here? We have half mass of the wooden block times its velocity squared, no? And then plus half mass of the bullet times its velocity squared. So that is what happened initially. And then finally, we have half times the mass of the bullet, mass of the, actually let's start with the wooden block, plus mass of the bullet. And then we have that velocity squared. Okay, and let's see what happens then. So this is going to be 0 because the wooden block was stationary. And then here we have half, mass is 0.05. The velocity there is 200 squared. We'll work out what the answer is. On this side we have half, 0.15 plus 0.05, and the velocity of that system is 50 squared. So let's go ahead and solve. So we have 0.5 multiplied by 0.05 multiplied by 200 squared. We have 1,000 joules. Remember, this is energy now. And then we have 0.5, 0.15 plus 0.05 multiplied by 50 squared. And we have 250 joules. So what does that tell you? It is non-elastic or inelastic. Yes, inelastic. Let's stick to the terminology that is used. Okay, so therefore, because, okay, so this is inelastic. Okay, because the sum of the kinetic energy initially is not equal to the sum of the kinetic energy at the end. Okay, and we can leave it at that. We have proved it with questions. With the working out that we did. Now 4.4. So it says, on a different occasion, a bullet is fired closer to the wooden block at the same velocity. Okay, so we still have this 200 meters per second. And it exits the block with an upward velocity of 195. So it ended up going up there, and we have it at 195 now meters per second. Okay, so if the net force exerted by the block on the bullet is 5 Newton downwards, okay, so there, calculate the time it takes the bullet to exit the block. Alright, so you're going to use your equation that has to deal with the net force and time and change in momentum. Let's just have a look. So basically, net force times delta T is equal to delta P. And what are we looking for? We're looking for the time, right? Yeah. Calculate the time it takes for the bullet to exit the block. So delta T would be equal to delta P over the net force. Now what is delta P? Basically, P final minus P initial. And the net force, because it's downwards, it's going to be -5, right? Our final momentum, so mass is still 0.05 multiplied by the final velocity, which is 195, minus the initial 0.05 times 200 divided by the -5. You can actually take the common factor of the mass out, and you're left with the 195 minus the 200. And then otherwise just put everything in the calculator as is, just to avoid silly mistakes. Okay, so now the time it takes is 0.05. Let me write that 5 like this in the seconds so that there's a you can distinguish between the 5 and the S. And that's it, and we're done with question 4. Alright, question 5. An ice skater of mass 53 kilograms moves on a frictionless surface AB. So here we do not have friction. Frictionless surface AB with a velocity of 6 meters per second. So here we are at 6 meters per second. and then slides up a rough inclined surface. So here we definitely have something, until coming to a stop at point C, 1.5 meters above the horizontal. The angle between the incline and the horizontal is theta. Alright, now it says 5.1, state the work energy theorem in words. So yeah, this is theory that you need to learn. Basically, the network, or the total network done, is equal to the change in kinetic energy. Okay, you can actually see it in the formula sheet. If you forget these definitions, please go to the formula sheet. Looking at the formula, work something out. Do you see? Network, there it is. The network done by a force, or by a net force, is equal to the change in kinetic energy. Again, there you have it. So going back to the question 5. There it is. We're done with 5.1. Now 5.2 says, draw a labeled free body diagram showing all the forces acting on the skater at point C. Okay, so C, let's just say this slope continued all the way up, right? C is here. Let's say this is point C. They didn't say this is now the edge. It's still there, point C. So there's the skater at point C. Of course, we have our gravitational force, definitely including our normal force over there. And because there is friction, how many marks is this? 3. Yes, because there's friction, this person is going up, right? So the friction is opposing the motion. But let's think about it. So at point C, they're stationary. They're not moving up. All right. So what is the temptation? The temptation, if you are stationary, the temptation is to fall backwards. So what will friction do? Friction will want you, it's opposing your motion. So once you are still, your tendency, because the slope is going down to the left, towards the left, going down, when you are actually this should be the other way around. Because at point C, this person is stationary, they're not moving anymore, and the temptation is to go in that direction. So friction will oppose that intended motion, or the motion in itself. And that is why they are still. I wouldn't even say it's Fk at this moment, because that's kinetic friction. It's basically, this one is Fs. Okay, so yeah, that was a tricky one, because I mean the temptation here is to draw it going downwards to the left. But anyway, those are the 3 marks. Okay, and then 5.3 then says, explain the term non-conservative force. Remember, it deals with that thing of, is it dependent or independent of the path taken? But in this case, with a non-conservative force, it's basically a force for which the work done is dependent on the path taken. Okay, like your friction force is dependent on the friction, on the path taken, not on the friction. So 5.4, for 6 marks, calculate the angle theta of the slope if the skater experiences a frictional force of 20. Okay, so this is now the kinetic friction, all right, not the static friction. So yeah, frictional force of 20 newtons while skating up the slope. Okay, so because we spoke about a non-conservative force, I will look for the equation that deals with the non-conservative force, which is the work done by the non-conservative force is equal to the change in kinetic energy plus the change in potential energy. I like using EK and EP actually. Alright, so this non-conservative force, remember, work is force, and before I leave the formula sheet, work is actually equal to the force times delta x times cos theta. Okay, and then we have half mass, so final velocity squared minus initial velocity squared. Please do not write this. It's not the same. Those two are not equal, okay? Do not make that mistake, or else everything is going to be incorrect. Your answer here will be incorrect if you do that. So now with the change in potential energy, we have mass times gravitational force or gravitational acceleration, final height minus initial height. Whew. Okay, so our kinetic energy is 20 Newton. Delta X, oh my gosh, we didn't actually, let's just go back to the question. I don't know what that is. Valid as, there we go. Okay, so we have 1,5 there, right? And we have theta there. So this will be my delta X. So what can I use there? I'm going to use sine. So sine theta will be equal to 1,5 over delta X. Therefore, delta X is equal to 1,5 divided by sine. Why am I saying 30 degrees? I wish it was 30 degrees. So basically, delta X, I have 1,5 over sine theta. Okay, now we have two thetas. Ooh, I probably should have not used theta for the second one because theta has already been defined. Maybe let's go with alpha. So what is our alpha here? Remember this non-conservative force, friction always acts in the opposite direction of motion. So then it will be 180 degrees. Then we have half the mass. The mass of the skater is 53 kilograms. The final velocity will be 0 because she comes to a standstill. He or she. Alright, and then the initial velocity is 6. So 6 squared. And then we have plus, the mass is 53, we have 9,8. Final height is 1,5, initial height is 0. So, yeah, we need to, what are we solving for again? The angle. Alright, you know, you can be so busy calculating and you're like, what are we doing? 20 times 1,5, that's 30. And times cos 180, that would be negative 30, right? But let's just put it there. So we have negative 30 over sine theta. Then we have 0,5 times 53 times negative 6 squared plus 53 times 9,8 times 1,5. Okay, so we have negative 174,9. So basically, if I take sine to the other side and I take negative 174 to the other side, and then I work out what theta is. So basically the negatives will cancel out. Let's work it out. So arc sine 30 over 174,9. I have an answer of 9,8765. So basically, rounding off to 2 decimal places, I'm going to have 9,88 degrees. And that is it. We are done. See you on the next question. Question 6. Please don't forget to like our videos and subscribe to our channel. Now it says, an observer with a detector standing on the side of a straight road records the frequency of a police car siren moving in a straight line on 2 separate occasions. Okay, so probably when the police car is approaching and then when it's moving away. The police car moves at the same constant speed on both occasions. The results are shown on the graphs A and B. So we can see over there the frequency that was heard by the observer or the listener is 1,100, And then graph B, it was 900. So we can see approaching is graph A, moving away or leaving is 900, because as the sound approaches the observer or the listener, the waves are compressed. Okay, and if the wavelengths are compressed, it means the frequency has increased. And then the opposite happens, moving away. Alrighty, anyway, 6.1, state the Doppler effect in words. Okay, so basically the Doppler effect is the change in frequency, okay, that a listener or an observer hears. All right. Yeah, so the change in frequency, actually the sound frequency, they don't hear the frequency, they hear the sound. So it's basically the change in frequency of the sound detected by a listener, okay, because the sound source and the listener have different velocities relative to the medium of sound. In this case, I mean, the sound of in A, the speed of sound in A would be like what, 340, averaging from 340 to 360, something like that. But yes, basically that's the definition that you have to know of by heart. And 6.2, which graph, A or B, shows the police car moving away from the observer? So moving away, that is definitely graph B. Okay, and give a reason for your answer. That is because what has been observed in graph A, there it's higher, right? The frequency that is observed there. Okay, or we could say graph B shows the police car moving away. Okay, no. Put it this way rather. Okay. Or you could say the frequency recorded, this 900, is lower than the emitted frequency. So this being the emitted frequency, and that's the recorded frequency. Okay, so that's that. Then 6.3, calculate the speed of the police car. Okay, so I'm going to look at the scenario of when it moves towards the listener. Okay, and I'm going to have to check out on the formula sheet what the formula is, because I do not know it in my mind. Okay, did I miss it somewhere? Most definitely did. So the frequency of the listener is equal to the speed of sound in A. I'll get to the signs there, and then the speed of the listener, or the velocity of the listener, and that of the source. Okay, so that is the formula. Where are we? Yeah, so the speed of sound in A is 314 meters per second. Okay, anyway, so if you're moving towards, if it's moving towards the listener, all right, what do you use in the denominator? You do the opposite. You would think towards would be a plus, right? But it's actually a minus in the denominator, and then whatever you have at the denominator, you have the opposite in the numerator. Okay, that's how I remember it. So what do we have? We have 340. Okay, plus, because this observer is standing, it means that the velocity is 0, so I'm not going to write that 0. But in the denominator, we have 340 minus, that's what we're looking for, right? The speed of the source, which is the speed of the police car. And we're going to multiply it by the frequency of the source. We actually don't know that either. We don't. Okay, but we do have the frequency of the listener, so that's 1100. Okay, so that's basically that. If I were to write this equation in terms of Fs, I see I have two unknowns, so I'm going to need another equation. But if I'm going to just write it in terms of the frequency of the source, I'm just going to say 1100 multiplied by 340 minus the velocity. Guys, if you get this wrong, if you use a plus instead of a minus, it does change your answer ultimately. So please make sure you know which is which. Okay, and then when it moves away, still same formula. So we have the velocity, because we've established that the velocity of the listener is actually 0. So here, because it's moving away, at the denominator we're going to have a plus. Okay, it does the opposite. On top it would have been a minus, but I mean the velocity of the listener is 0. Anyway, the frequency was 900 of the listener. And then we have our 340 over there, and 340 plus speed of the car. And then we have the frequency of the source. So if you write this is my equation number 1. If I write this in terms of the frequency of the source, I'm going to get 900 multiplied by 340 plus the speed of the source divided by 340. So then I'm going to say, the frequency of the source is equal to the frequency of the source. Basically, 1,100. 340 minus the velocity divided by 340 is equal to the 900. 340 plus that divided by 340. So the 340s are gonna cancel out, right? If I multiply by 340 on both sides, they're going to cancel. But now I want to know what is 1,100 multiplied by 340. So I have 374,000 minus 1,100 speed of the police. And then we have 900 multiplied by 340, which is 306,000 plus 900 speed. So if I take 1,100 to the other side, I will have 900 plus the 1,100, so that's 2,000. And if I take 306 to the left, so I have 374 minus 306, and that's 68,000. So basically, the speed of the police car in this case is 68,000 divided by 2,000. And that is 34 meters per second. Whew, it must have been going quite high. Probably exceeding the speed limit. Okay, so that is 6.3. Now 6.4, what do we have there? We have the emission spectra. So study the emission spectra A, B, and C of a distant star as observed from Earth. Spectrum A is the lab reference spectrum of the same star. So that's basically like our reference point. Okay, so 6.4.1, which spectrum, B or C, indicates that the star is moving away from the Earth? So how do you know? If it's moving away, it means your wavelength is increasing, right? And if the wavelength is increasing, we're looking at the blue shift. If it was moving towards, then your wavelength would have been reduced, and therefore we'd be looking at the blue shift. So how do we know if it's a red shift? If it's a red shift, remember they've shown you where the red region is and where the blue region is. So the red shift is moving more towards the red region. Blue shift moves more towards the blue region. So what's happening here? Which one indicates that the star is moving away? So basically looking for the red shift. And I can see that B is actually moving towards the red region, whereas C is moving towards the blue region. So B would be my answer, because it has shifted to the red region. It's a red shift. And so if the blue part, if you don't understand this section, please do look at the link that I've attached that explains under the topic of Doppler effect, the red shift and blue shift. Okay. Now, if the blue part of a star spectrum is being observed from Earth, okay, describe the frequency and the wavelength. Okay, I've already spoken about the wavelength. So describe the frequency and the wavelength of this light. Basically, the frequency would be high as the wavelength is actually low. So shorter wavelength, higher frequency, basically. And that's it for question 6. All right, question 7. So 2 point charges A and B are placed 3 meters apart. The charge on A is 6 microcoulomb and the charge on B is -3 microcoulomb. P is a point 1 meter to the right of charge B. Okay, so we can see there's A, there's B, and there's P. Now 7.1, define the term electric field at a point. Alright, so electric field at a point is basically the electrostatic force experienced per unit positive charge. That's very important, okay? It's an electric field, electrostatic force experienced per unit positive charge placed at that point. And like I said, if you forget the definition, just go to the formula sheet, have a look at it. Okay, electric field at a point. So here we are. Okay, so the electric field at a point is the electrostatic force experienced per unit positive charge placed at that point. Okay. Yeah. And then let's get to the question. Question 7.2. Calculate the net electric field at a point. Okay, so I shouldn't have left the formula sheet, but the net electric field at a point basically is the sum of all the electric fields. Okay, so electric field according to A and the electric field according to B, right, in relation to P. So A in relation to P and B in relation to P. So at this point, you see there are 5 marks there. You need to know, they didn't ask for this, but you need to know how the electric field lines are going to go. Alright, so on your question paper or somewhere on your answer sheet, just draw the electric field lines for yourself. So with the positive one, we know that it's pointing outward. With the negative, it's going in, right? And yeah, so it's basically going in. There we go. Actually, it's going to be more like this. Alright. There we go. They're all going in. You don't even need to draw the others. It's just really to see what is going on over there. But you could have done that as well. All of them are going out. And here they're going in. Okay. But you get the point. So, how does that help us in terms of getting the net electric field? Well, I know that A in relation, if I choose going to the right as positive, A in relation to P is positive. Okay, so I will have a positive. And remember, according to our definition, the electric field at a point is the force per unit positive charge. Okay, but I'm not going to really use that formula because we don't have the electrostatic force. What we are given rather, or what we have rather, instead of this, you know that, the force is equal to K, Q1, Q2, and all of that. So I'm going to substitute that into F. And instead, we're going to use this equation. Okay, so we have K, Q, A in relation, well, in this case it's A, and then over R squared, and that is positive. Okay, now let's get back and look at our charge B and C. So B in relation to P, do you see it's going in the opposite direction? So that has to be negative. Okay, so if you don't know how to get which one is negative, which one is positive, your electric field lines will assist you in that regard. Okay, so K is 9 times 10 to the power 9. The charge on A is 6. So here, please do not put in the sign. Okay, take it as positive for both A and B. All right, and then the distance from A to P, so we have 3 meters between A and B and an extra meter over there, so basically it's 4. Whew, this is messy. Okay, you got it right, the electric field lines. I just want a neat sketch here. So here we have 4 meters, and then so we're gonna put 4 squared, and then minus 9 times 10 to the 9. The charge on B is -3, but we're not gonna put that negative. And then we're dividing it by the distance between B and P is 1. Okay, so we're going to put all of this in the calculator and see what we come up with. So we have our fraction over there. So 9 times 10 to the 9 times 6 times 10 to the -6 all over 4 squared, which is 16, minus 9 times 10 to the 9 times 3 times 10 to the -6 all over, that's just 1. Okay, so we're getting a charge of negative 23,625. So what is the unit? Remember, it is force per unit positive charge, so force is Newton per charge. Now, what do they want? So the net electric field. So because we have a negative here, you could just say this is the magnitude, 23,625, and that negative just means it's to the left, right? Because we chose the left as negative. Okay, now I left out the unit. Newton per coulomb to the left. All right, so that's 7.2. Now 7.3. A proton is placed at point P. Calculate the magnitude of the initial acceleration of the proton if the mass of the proton is 1,67 times 10 to the -27. What came to my mind when I read acceleration and when I read mass is force, electrostatic force, being equal to the net electrostatic force, mass times acceleration. And that force, remember we said that the electric field at a point is the electrostatic force per unit positive charge. So if I want the force has to be equal to the electric field at a point multiplied by the charge. Okay, so in this case, the electrostatic force is equal to the net electric field at point P multiplied by the charge. All right, and that's equal to mass times acceleration. So let's just see what we can put in there. What we calculated was the 23,625, right? And then what is the charge on a proton? Do you know? Okay, before I even, let's just do this. What are we looking for? We're looking for acceleration. So let's just write this in terms of acceleration. Acceleration is EQ over mass. What is the 23,625? What is the charge on a proton? Well, if you know the charge of an electron, the proton will just be the positive of that. Okay, so the charge on an electron is -1,6, so a proton will be positive 1,6 times 10 to the -19. All right, still with me there? And then the mass is what they have given us, right? So let's just go up, up, up again and read that. Okay, so they told us that the mass is 1,67 times 10 to the -27. All right, and then now we can calculate what the acceleration is. So let's just have a look there, the calculator. So we have 23,625 multiplied by 1,6 times 10 to the -19 all over 1,67 times 10 to the -27. This calculator. I always forget to make sure that it gives us answers in scientific notation. Okay, I am going to say 2, 26, and then count, times 10 to the 1, 2, 5, 6, 7, 8, 9, 10, 11, 12, times 10 to the negative 12. No, not negative. Positive. This is a very big number. What is it? Is it a... Definitely not... Yeah, trillion, I don't know, billion, whatever. But it's a positive number. So 2,26 times 10 to the power 12. Alright, that's the unit meters per second squared. And that is expected. I mean, electrons, protons, they move wild. We can't see them with the naked eye. So that for me makes sense, that it is that fast. Okay, so they wanted the magnitude of the initial acceleration, and that's it. And then now 7.4, it says if an electron was placed at point P instead of a proton, okay, so electron, now the charge is negative, how would the acceleration of the electron compare to that of the proton? Are you expecting an electron to be faster than a proton? Well, looking at acceleration, right, force is equal to mass times acceleration. So we know that acceleration and mass are inversely proportional to each other. Okay, so if the proton had a mass of 1,67 times 10 to the negative 27 kilogram, how does an electron compare? Because they have a similar charge, just opposite. One is negative, one is positive, right? The mass of an electron, okay, the mass of an electron is basically 9,11 times 10 to the power negative 31, okay? Whereas the mass of a proton is 1,67 times 10 to the power negative 27. Which one is heavier? Please don't be fooled by the big number. There's a negative in front. The mass of the proton is heavier than the mass of an electron. Okay, so since the electron is lighter, we are expecting the acceleration to actually be larger. Let's just go back to the question to make sure that I'm answering it. If an electron was placed at point P instead of the proton, how would the acceleration of the electron compare? The acceleration will definitely be bigger because the mass is smaller than the proton's mass. All right, and we are done with question 7. Question 8. A battery with unknown EMF and an internal resistance of 1 ohm is connected to 3 resistors, a light bulb, so here are the 3 resistors, a light bulb, a high resistance voltmeter, a switch, and an ammeter of negligible resistance as shown below. The resistance of the light bulb is 4 ohm. And the resistance of the 3 resistors are 2R, R, and 6R respectively. Okay, so there we go. So we don't know what the EMF is. And then the internal resistance is 1 ohm. So let's just take note of that. Now 8.1, it says define the term EMF. Now we're seeing a trend with these theoretical questions, right? They can only ask so much, so please make sure that you know all of them. So the term EMF, how I would say it is, basically it's the maximum energy that a battery provides, okay? It's the maximum energy per unit charge that a battery provides, all right? And then 8.2, it says when switch S is closed, the current through the ammeter is 0.2 amperes. And the potential difference across R1, okay, is 6 volts. So if we had a voltmeter there, it would read 6 volts. Now it says for 8.2.1, write down the value of V2. Okay, so you have now, well, voltmeters that would be in series, right? how would we or rather, how would we deal with this? You had a particular current. We don't know what that current is, but as soon as it got here, it split. Part of it went there, and another part of it went this side, which is 0.2 amperes. Okay, so, and it's only 1 mark, by the way. So if we have a look at these resistors as well. Here you have 2R, and there it's just R. Okay, so let's just say a scenario, just entertain me if you may. If we assume that the total current is 2, let's just say we have a current of 2 amperes passing through here. All right, yeah, assumption. We're gonna get to the answer right now. Some of you already know it because it's 1 mark, you can see it quickly, but let's assume we have a current of 2 amperes. Okay, this current will pass through this 2 ohm resistor, and the very same current of 2 amperes will pass through that resistor R. Okay, and we know when it passes through R1, we have voltmeter reading of 6 volts. Okay, so you have 2 amperes and 6 volts. It means this R1, 6 divided by 2, we have 3 ohm. Okay, now when it passes through R2, we still have we still have the same 2 amperes passing through. All right, and now this resistor is half. Initially we had 2R, right? Okay, let me see. 2R would be equal to 3 ohm. Therefore, R would be equal to 1,5 ohm. Okay, so now we still have the same 2 amperes. And what would pass through resistor R2? We know that R2 is actually equal to R. So basically, going through R2, we have 1,5 amperes. Now, what would be the voltage? 1,5 times 2 ohm would be 3 volts. Okay, so sometimes just assume a number and just work it out in your mind, even though it's 1 mark, just so that you understand what you're doing. But ultimately what I'm getting to here, you had twice the resistance, and that's 6 volts. Now you only have 1 resistor there, so we're gonna have 3 volts over there. Okay, so your answer basically for 8.2.1 is 3 volts. 8.2.2, write down the value of the current through R2. Okay, we'll get back to that. Okay, so here we have 6 volts, there we have 3 volts. We have current, the total current here, current there, current there. So now we want the value of the current through R2, which is the same current moving through R1. Okay, but remember we had this total current. I'm going to say IT for total, which was equal to the current going through, I'll just say R2, as well as R1, plus the 0.2 amperes. Okay, so let us see how we can work that out. Now, remember through R3, I'm now looking at this current here, which is 0.2 amperes. Okay, so there R3 we have 6R, right? And if through this 6R we have 0.2 amperes passing through, how much would be passing over here? Okay, through, okay, let me put it this way. The current passing through here, the resistance that it goes through is basically 6R. The current going through here, the resistance it's going through is R, 2R plus R, which is 3R. Sorry guys, I'm distracted by the little one. So basically the current passing through here goes through 3R. The current going through here goes through 6R. We are expecting less of the current to go through 6R because the resistance is quite high, meaning the current reading is low. But here I'm expecting the current actually to be a bit higher. And how much higher? I hope you see here we have 6, which is double that. So I'm expecting the current to actually be double, twice. Okay, so the current through R2 will actually be 0.2 times 2, which is 0.4. Okay, I hope that makes sense, guys. So basically, current through R2 is basically 0.4 amperes, and this total current then becomes 0.6 amperes out of interest, but this is what they wanted for 1 mark. So it's just, this question is just really relating and looking just at ratios basically. And if you don't still understand this, I'll try to build a model. I'll see if I have time through that Phet simulation. We can do this and look at it again. Okay, but let's just go through the other questions and I'll see if I have time to go through the model. So 8.3, calculate the resistance of R3. Okay, I've written a whole lot here. Okay, so we've established that here we have 0.6 amperes. Over here we have 0.2 amperes going through here, 0.4 amperes. Here we have 6 V. Yeah. So anyway, it's saying calculate the resistance of R3. So what we're going to do there, let's just first... Okay, girl. And that's, yeah, that's 3 marks. Let me just pause. All right, let's try again. I try to make sure I do these recordings before coming home, or else it's not really that possible. Anyway, calculate the resistance through R3. So there is R3, right? So we know our current going through there is 0.2 amperes, right? And what else do we know? We know that our resistance is 6R. Okay, what is the voltage? Okay, that's where I would start basically. All right, if I can get the voltage, then I can work out what the resistance is. So I know that the voltage here, remember when you have voltmeters in series, you can actually add them. Okay, so with the current going through here of 0.4, the total voltage there would be 9 volts. All right, and we know that voltmeters in parallel are actually equal. All right, so on the top part we have 9 volts, so even here it means we also have 9 volts. So I hope you see where that comes from. Voltmeters in parallel are equal to one another, so the voltmeter reading is the same for those components in parallel. So we have 9 volts, and we know through Ohm's law that resistance is actually voltage over current. Okay, and our voltage is 9, our current is 0.2. But remember, yeah, so they wanted the resistance of R3, which is 6R. So I'm just going to say R3. Okay, so if you take out the calculator and you say 9 divided by 0.2, we actually get 45 ohm. Alright, so that is the resistance of R3. Okay, if ever we wanted R, we can actually calculate it. We know that R3 is actually 6R. This is not asked, by the way. And so 6R would be equal to 45. So basically R would be 45 divided by 6. That's 7.5 ohm. Yeah, so R is actually 7.5. Remember that scenario I made up here? I assumed. So please don't think R1 is 3 ohm and R2 is 1.5. That was just an assumption. So now we know R is actually 7.5. I'm actually going to write that down. And we have 2R as 15 ohm. And yeah. But anyway, the answer is 45 ohm. Alright, and then 8.4, it says calculate the value of the EMF. Alright, so we know EMF is equal to the current, and then we have the external resistance plus the internal resistance. Or we can just have big R and small r. Let's just rather put it like that. Big R and small r. So what do we have there? We have the internal resistance, right? It is 1. They told us at the beginning. We have the current, total current, it's 0.6 amperes. Now we just need the external resistance. And what does this external resistance consist of? Well, we have R1 plus R2, which is parallel to R3. Okay, so basically let's just say we have the parallel resistance, and then we have this light bulb over here. So that 4 ohm. All right, so let's just sort out what this parallel resistance is. We have 1 over R parallel, and then we have 1 over 15 plus 7.5, and then we also have 1 over 45. All right, so let's just work that out. I have 1 over 7 plus, 7.5 plus 15, and then plus 1 over 45. So if I take that answer and I say 1 divided by the answer, I get 15. So we have 15 over there. So then the R external would be the 15 plus 4 ohm, which is simply 19 ohm. Okay. Yes, my baby, we are almost there. So EMF is equal to the total current, which is 0.6. External resistance is 19. Internal resistance is 1. So basically, we have 0.6 multiplied by 20, which is 12 volts. Baby girl, you're teaching them. Yes, that's right. So we're done with 8,4 and now 8,5. Alright, 8,5 says in a separate circuit, a variable resistor. Let me pause. In a separate circuit, a variable resistor is connected to a battery with an unknown potential difference as seen in the following diagram. The graph below shows the relationship between the power dissipated in the resistor and the resistance of the resistor. So we can see power on the y-axis and the resistor 1 over R on the x-axis. So now it says use the graph to determine the potential difference across the resistor. Okay, we're looking for V. Now if I look at the equations for power, I know that power is equal to V times I. Alright, but we don't have, we're looking for V here, right? We don't really have current, we have resistance. So I'm gonna write this V in terms of I and R. So IR times I. Okay, so that's where we get the equation I squared times R. Alright, so now if I do that, okay, let's park that. Let me look at the gradient of this graph. The gradient of this graph will be delta P, because it's delta Y over delta X. So delta P over delta 1 over R. Okay, and if I do that, like I said, with power, I have I squared times R. I don't really have current, nor do I have the voltmeter. Maybe I shouldn't have changed it. Let me just keep it to VI. Let's see where that takes me. Okay, because I'm looking for V ultimately. Let's see. So I have VI. No, let me take it back to just R. I'm confusing myself. What's the other one? Do I have V and R for power? Let's just see. Yes, yeah, because with I, I'm not going to go far. So let's say V squared over R, because I want V, I have P, and I have R. So I want an equation with V squared and R, not I. So P, delta P would be V squared divided by R all over 1 over R. Okay, simply put, I have V squared over R divided by 1 over R, and we know that we can turn that around and say multiplied by R over 1. And essentially my gradient is V squared, which is great. Now let's go get the gradient. Okay, so I'm just going to take the points, the beginning and the end, just to make things easy for myself. So in terms of power, I will have final minus initial. And in terms of 1 over R, no, that's not power. In terms of power, I will have 1,000 minus 0. And in terms of 1 over R, I will have 10 minus 0. Okay, and that's V squared. So 1,000 divided by 10, that's simply 100. And then if I square both sides, I'm not going to consider the negative answer. I have that V is actually 10 ohm. Yo, 10 volts. My goodness. 10 volts. Okay, so there it is. Let me try to set up that this cell over here, and let's just see how it works out. So here we are on the website. We're going to go to physics. If this thing is going to take long, I'm just not going to finish it off. You have to try it by yourself because practice makes perfect, right? All right. So my internet is a bit slow, but here we are. We're going to look for an electric circuit. And we're going to go to the construction kit. There we go. And while we're waiting for it to load, just gonna click on play, and it should give you an empty sheet so that you can start there. Okay, there we go, AC voltage, and there we are. Whew. We're gonna construct a bit here. So we have a wire. We can expand it a bit, and then let's just add a battery. And you know the way it's showing us here, so this battery, I hope you can see, the positive is actually on the right and the negative on the left. So maybe let's just swap a bit there. Okay, now my thing has, okay, it has frozen. Let me just set it up and then I'll continue the lesson. Okay, so this page has become unresponsive. I think it's the network at the moment since we're out of electricity. So yeah, I'll do this another time. I think let's just move on to the next question. Question 9. We're almost there. So it says, study the diagram of a simple generator below and answer the questions that follow. So I see here we have that diagram. We have these slip rings. Okay, so it's going clockwise. Okay, cool. Now 9.1, it says, is this an AC or a DC generator? If you cannot tell the difference, ask yourself, if I have a split ring, which we do not have in this case, do you see this looks like a C, this looks like a D? So a split ring is for a DC generator in this case, or a DC motor. Alright? So in this case then, we definitely have an AC generator. And give a reason for your answer. It's because of the slip rings. Alright, so now it says, state the energy conversion that takes place in this generator. And with a generator, we're trying to get electricity, okay? I think Eskom has taught us that through load shedding. So because of that, we go from mechanical energy to electrical energy. Alright, so mechanical energy to electrical energy, that's the energy conversion. And the 9.3, in which direction will the induced current flow? State only from A to B or from B to A. So because this is north and that's south, your index finger will point, remember we're using the right hand rule, right? So your index finger on your right hand rule will point to the right. So basically your finger will look something like that. And then, because we're going clockwise, if I'm looking at this point over here, your thumb will push it upwards so that it goes clockwise. Okay, so there's your thumb. And then you have the rest of the fingers, right? But you have your middle finger, which is pointing somewhere. Okay, let's say that's your hand. So your middle finger, if everything is at 90 degrees to each other, your middle finger is actually pointing inside the page. Okay, so it's going in, all right? This is the middle finger over here. It's going inward, all right? And if that's the case, then it's going from A to B. All right, so we're done with that portion. And then 9.4, so before we get there, it says the diagram shows the EMF time graph for one complete rotation of the coil. So it takes 0.2 seconds for a complete rotation of the coil. This 150 would be your V max, right? And if we were to get the root mean squared, it would be somewhere around there. So anyway, 9.4 says, calculate the resistance of the load RL if the value of IRMS is 4.55 amperes when the Vmax is 150. Okay, so in order for us to get the resistance would be equal to V over I. Okay, but we do not have the current here. We have the IRMS or RMS current. So in that case, we cannot use Vmax, but we have to use VRMS. Okay, and what is VRMS equal to? It's basically, let's look at the formula sheet. VRMS is equal to Vmax over root 2. Okay, so going back to our calculation over here, we're going to say VRMS is Vmax, which is 150, divided by root 2, and IRMS is 4.55. So if we calculate that, we get 150 divided by root 2 all over 4.55, and that gives us 23.31 ohm, because we're looking for resistor L. Alright, now 9.5, it says load RL is now replaced with a bulb with a power consumption of 400 watts. Assume that the bulb is 100% effective and calculate the light energy. Okay, energy, something in joules, emitted by the bulb in 3 minutes. Okay, so in 3 minutes, that would be 3 times 60 seconds, because we need to work with seconds. So that's 180 seconds. And we know our equation that power is the work or the rate at which work is done. So basically the work or the energy of the light bulb would be power multiplied by the time. So we have 400 watts multiplied by 180 seconds, and we get 72,000 joules. Okay, and now 9.6.1. So it says the speed of rotation of the coil is now doubled. Okay, if it doubles, what does that mean? It means your Vmax, it doubles, and also it takes much quicker time. Okay, so in order to complete one wave, you don't take 0.2 seconds anymore. You're going to take half that time. Okay, so it's going to be 0.1 seconds to complete the full wave. Now it says redraw the above diagram in your answer book. and on the same set of axes indicate the old and the new pattern obtained. Okay, so let us now draw this graph. There we are. Okay, so the original one looks, okay, maybe let me not draw it like that. The original one looks like that, and at this point we have 0,2. This is time in seconds, and that's EMF in volts. Okay, so let's use a different colored pen. So what happens, like I said, your EMF doubles. So if we had 150 there, if this is now 150, and that's negative 150, let me just expand this so that, yeah, we're not limited. So now we're going to go all the way to 300. Okay, I have Dora the Explorer with me here. So we have 300, and then the period of the graph would have reduced. So instead of 0,2, we will now look at 0,1. So I need to fit that graph there. Okay, so how am I going to draw this? So halfway through, I need to have reached there, and again I would have had to reach there. So let's see, let's draw this new graph. So yeah, no, I didn't draw that correctly. This should be at negative 300. Okay, so there we are. Ooh. Okay, so that's how it will look. Alright, and that's for 2. And finally, 9,6,2. With what factor will the energy emitted change if the speed of rotation of the coil is doubled? Okay, so yeah, like we said there, so power is the rate at which work is done. Okay, and now thinking about energy, we have power times delta T. And power, because I know that the EMF will double, I'm going to use power in terms of, let's just look at the formulas. Okay, so power can be VI or I squared R or V squared. Okay, so V squared over R delta T. Alright, so let's hold on. Okay. Alright, so what am I trying to get at here? So I know that in this case that the work is actually directly proportional to V squared. And I know, actually looking at my graph over here, that it has actually doubled. Alright, the EMF has doubled. So if it has doubled, that would be squared, and the resistance wouldn't change. Not expecting time to change as well. So as a result, well, now actually the time has been halved. Okay, so the time it takes to complete one wave, once the coil is doubled, it's actually halved. Alright, so yeah. So the time there is halved. Now, what would 2 squared be? That would be 4. Okay, then I still have my V squared over R. That's in terms of power. And then we also have the half, which is delta T. So ultimately, the 4 times a half, that's 2. And that goes back to P delta T, because this is P. So what is the factor? With what factor will the energy emitted change if the speed of the rotation of the coil is doubled? Well, basically that would be 2 times. Alright, And that's it for question 9. And the last question, question 10. So, in an experiment, different light sources are shone onto the surface of an unknown metal. Okay, so 10.1, explain the term work function. Alright, so work function is basically the minimum energy that an electron in the metal needs to be emitted from the metal surface. Okay. And then 10.2, electrons with a maximum kinetic energy of 1.2 times 10 to the negative 19 joules are emitted from the surface of the metal when ultraviolet light with the frequency of 6,3 times 10 to the 14 hertz is incident on it. Calculate the work function of the metal. So I would go to the formula sheet, have a look at the equations available with work function. So I have that E is equal to work function plus the kinetic or the maximum kinetic energy. Okay, so if we go back to it, we need the work function. So basically the work function would be the energy minus the kinetic energy, maximum kinetic energy. And that energy is basically Planck's constant multiplied by the frequency minus the maximum kinetic energy. They gave us the kinetic energy, maximum kinetic energy, which is 1,2 times 10 to the negative 19. They also gave us the frequency, and we have Planck's constant here, which is 6,63 times 10 to the negative 34. The frequency that we have over there is 6,3 multiplied by, or times 10 to the 14, minus the maximum kinetic energy, which is 1,2 times 10 to the negative 19. So let's just work that out, and we're going to get the minimum energy that we need. So we have 6,63 times 10 to the negative 34 multiplied by 6,3 times 10 to the 14 minus 1,2 times 10 to the negative 19. Okay, so we're getting an answer of 2,98 times 10 to the negative 19, and that's joules because we're dealing with energy. Now 10.3, it says, will electromagnetic radiation with that frequency, 3 times 10 to the 16 hertz, emit electrons from the surface of this particular metal? Remember, this is our minimum energy that's required. So let's see, can that frequency emit? Okay, so we're going to have to do some calculations here in order to show, right? So I would say then, yeah, let us work out what the frequency would be. Okay, the threshold frequency. So if this threshold frequency, so what I'm trying to get the threshold frequency. If this threshold frequency is bigger or it's smaller than the frequency that is used to emit the electrons, then we know it's a yes. Okay, but if this threshold frequency is bigger than the frequency that's given, then the electrons will not be emitted. Okay, so let's go ahead and calculate this threshold frequency. I'm looking at our equations over there. We know that the work function is equal to Planck's constant times the threshold frequency. So we're working out what the threshold frequency would be, which is the work function divided by Planck's constant. We already worked out the work function, which is 2,98 times 10 to the negative 19. And Planck's constant is 6,63 times 10 to the negative 34. So let's work that out. So we have Oh gosh, so our answer there, no, it doesn't have that answer. 2,98 times 10 to the negative 19 all over 6,63 times 10 to the negative 34. Sure. Why does this calculator do this? Okay, so we have 4,49 times 10 to the power 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 times 10 to the 14. So these are hertz. And is it bigger or is it smaller? It's definitely smaller than the frequency. So our threshold frequency is smaller than the frequency of that electromagnetic radiation. So therefore, will it be able to emit the electrons? Yes, it will. Okay, 10.4. When the photoelectric effect is demonstrated, a negatively charged plate is used. Okay. Explain why when ultraviolet light is shone on a positively charged plate, no charge is lost by the plate. Okay, so basically when we do or we're demonstrating this photoelectric effect, you shine the light on the metal, the energy from that light, right, with enough frequency, if the energy is just the work function or higher than the work function, and also if the energy, okay, and also if the frequency is higher or just equal to the threshold frequency, then the electrons have enough energy then, okay, to get woken up from sleep, from rest, and then with enough kinetic energy they can move and be ejected from that metal surface. So here, what it's telling us, if this metal plate is positive, okay, you have a metal plate, it is positively charged, and you have these electrons which are negatively charged. Do you think these electrons are going to want to leave? No, they will be attracted to this positively charged plate over here. And that is why ultimately, guys, I'm not going to write this down. I'm realizing I'm talking a lot. So ultimately, there will not be any charge that is lost by the plate, because these electrons will be attracted to the positively charged plate. And like they said, normally a negatively charged plate is used. And when that is used, the electrons are happy to leave because the same charge repels. But because now we have opposite charges, they will attract each other. And that is why no charge is lost by the plate. All right. And basically that's it for question 10. And that's it for this paper. Thank you for tuning in.